Okay, part 2 of 2 of a analysis of a high-pass filter. Okay, we've added an oscilloscope to probe the voltages across R1 simultaneously with our input or source voltage V1. The voltage across the resistor is captured by channel B and is shown by the blue sinusoid or blue curve in the trace window. The source voltage is on channel A and is given by the green curve. Multisim allows you to change the color of the probe wires to help make the connections and data visually more clear. And you can see those colors on the circuit diagram to the left. The green sinusoid of channel A has a peak value that covers 2 vertical divisions. The oscilloscope shows us that each voltage division represents 500 millivolts. So 2 divisions are therefore 1000 millivolts or 1 volt peak. If we look at our symbol for the voltage source on the circuit diagram on the left, we see that it was designed to be 1 volt peak, so this checks out. Now note our blue curve has a different voltage scale. That is 50 millivolts per division. Channel B tells us the peak voltage is approximately 60 millivolts for the circuit parameters we've chosen, and the graph shows a peak value that is slightly more than 1 division, which represents 50 millivolts. We'll come back to more exacting calculations for the magnitude in the next slide. For the moment, I want to look at the phase difference between the blue curve, representing the voltage out, or the voltage across the resistor, and the green curve, representing the voltage source, or V1. Blue leads green. And this is exactly what our mathematically derived intuition told us would happen in the previous slide and last video. The fact that the peak of the blue curve appears to the left of the peak of the green curve means that it appears earlier in time than the green curve. We say the blue curve is leading the green curve. Moreover, the oscilloscope data is presenting both curves as a function of time. Since the blue curve is shifted to the left, we know that its phase angle is positive, or at least it is more positive than the phase angle for the green curve. Actually, we know the phase angle of the voltage source is 0 degrees. This was by design and is shown on the description for the circuit symbol for our voltage source. The phase angle is the third and last value and is 0 degrees. So, in fact, the phase of our blue curve is definitely going to be positive. However, the intuition I really want you to leave with is this. Positive phase angles shift the sine curve to the left, and negative phase angles shift the sine curve to the right. This often confuses beginning learners. If you need a refresher, I encourage you to consult videos on Sal Khan's Khan Academy. Now that we have some intuition about what to expect, let's calculate values for both our voltage magnitude and phase. The calculations may be the easiest part. We've rewritten equation 3 to present the imaginary term in the denominator in a notation that is a little easier to interpret. Our result is equation 4. Now, let's look at the magnitude of V out first. We have the ratio or quotient of 2 complex numbers. This simply is the quotient of the magnitudes of our phasor. The numerator's magnitude is simply R1, the value of our chosen resistor, which in this case is 1000 ohms. The denominator is simply a complex number. The magnitude of a complex number is derived through Pythagoras' theorem. That is, the magnitude is the square root of the sum of the squares of the real and imaginary terms. To confirm our circuit parameters, R1 is 1000 ohms, the capacitance is 0.01 microfarads, and the frequency of interest is 1000 hertz. Note, we've converted omega, the angular frequency, whose units are radians per second, into units of frequency using the formula omega is 2 pi times frequency, where frequency is given in hertz. When we plug in the values for our circuit parameters and divide the magnitudes, we get a result of approximately 62.7 millivolts peak. We can compare this to the measured value we get from our oscilloscope data. To do this, we must move the positions of our time cursors as shown as light blue and yellow vertical lines in our scope's window. Visually, we move the cursors so they overlap the peak values as close as possible. The peak of the blue curve is a little flat in our selected time scale, so a bit of patience is required when making the oscilloscope adjustments. And these have been done already. Now, we read the peak value of our voltage directly from the scope's data window. Since the blue curve is on channel B, and the cursor is the light blue or T1 cursor, we look at the intersection of channel B and T1. This value has been highlighted by the red arrows and reads approximately 62.7 millivolts peak. This is pretty solid agreement between theory and the simulated measurement. Now, for completeness, we can identify what the other values mean. The next value in channel B represents the value of the blue curve at the cursor for time t2, shown here in yellow. This value reads 6.187 millivolts, and this looks visually like about 0 millivolts on the scope's trace. Now, channel A data begins with the value of the green curve at time t1 captured on the yellow trace. This value is approximately 36 millivolts. Now, on the graph, the green curve appears almost 0 at the time t1 cursor. And this makes sense since each division for the green curve is 500 millivolts. Now, the second value for channel A is approximately 997 millivolts, or approximately 1 volt peak, and this is exactly what we expect. Now, we'll discuss the time difference data in the next slide when we calculate the phase angle difference between our blue and green waveforms. Now, to calculate our phase angle, we use a combination of phasor and Cartesian math for complex numbers. The numerator of equation 4 is simply the value of our resistor, and its phase angle is 0 degrees. An ideal resistor will have a 0 degrees phase angle. Real resistors, on the other hand, may show some phase terms due to what are known as parasitic inductances and capacitances. The oscilloscope would show these imaginary term contributions if they were present. The denominator of equation 4 is written in Cartesian form, and the phase angle of an imaginary number is the arctangent or inverse tangent of the imaginary term divided by the real term. When our circuit parameters are plugged in, we get a phase angle of negative 86.4 degrees for the denominator. Now, the phase angle we desire is the difference between the numerator and the denominator, which is 0 minus negative 86.4 degrees, which is positive 86.4 degrees. The phase angle of V out is positive, just as we expected. Now, we can compare our theoretical value to the value measured by our oscilloscope. The scope provides us time data. We'll have to convert time into a phase angle using the formula omega times t, or 2 pi times the frequency times t, to convert into angle data given in radians. The time used here is the difference between the time cursors given in our scope data as t1 minus t2. The value is approximately 238.6 microseconds and is highlighted by the red arrow on the left-hand side of the slide. And finally, when we convert our phase angle from radians into degrees, we find a measured value of the phase angle to be approximately 85.9 degrees. And again, this represents pretty good agreement between theory and simulated measurement, less than a 0.5% difference. So let's recap where we've been. First, we developed an intuition of the magnitude and phase across the resistor from the expected behavior of the physical elements themselves, that is, from the voltage source, the capacitor, and the resistor. Next, we calculated the magnitude and phase angle of our circuit for a given frequency of 1000 Hz and compared our answers to the measured data provided by our oscilloscope. And we showed that we had pretty good agreement between theory and measurement. Now, let's use a tool called the Bode plotter to provide the frequency response. That is, the magnitude and phase angles for a wide range of input frequencies, and not just 1000 Hz as used in our earlier example. This type of analysis is called an AC sweep and is used quite often in the design of new circuits. In our sweep, or scan of the circuit, we've inputted a range of frequencies from 20 Hz to 50,000 Hz. The calculations that we just did for 1000 Hz are repeated across the range of frequencies in our sweep range. Let's first look at the magnitude response for Vout. It starts at 0 volts peak and rises asymptotically to 1 volt peak, just as we described earlier. As frequency increases, the capacitor is behaving more like a short circuit, and therefore more of the voltage source appears over the resistor in our voltage divider circuit. Again, we also see the high-pass nature of this filter circuit. Voltages with higher frequencies appear across the resistor, and therefore this circuit is said to be a high-pass filter. Similarly, we can look at the phase response of Vout, the voltage across our resistor. As the frequency increases, the phase angle decreases. It starts at 90 degrees when the capacitor controls or opens the circuit and decreases to 0 degrees as the capacitor begins to behave like a short. At higher frequencies, the resistor controls the behavior of the circuit, and therefore the complex value looks more like a real number, R1, which has a 0 degrees phase angle.